Contributions of J. Thomson by Kirsten Taylor, Mariam Mohammed, and Toyini Dogan. Joseph John Thomson, often called J.J., was born in a suburb in Cheetham Hill, England, on December 18, 1856. His mother, Emma Swindles, came from a textile family, and his father, Joseph James Johnson, was the heir of an antiquarian bookshop founded by his grandfather. He also was the oldest of two sons. His brother was Frederick Vernon Thomson. His father wanted him to become an engineer at Sharp Stewart Company, but his father's life and plans for J. Thomson were cut short in 1873. Fortunately, afterwards, he was admitted to Owens College, now known as the University at Manchester, at the age of 14. There, he was able to take courses in experimental physics. In 1870, he obtained a scholarship to attend Trinity College in Cambridge. There, he received his B.A. degree in mathematics in 1880, which opened up the opportunity for him to research at the Cavendish Laboratory. Here, he became the Cavendish Professor of Physics and attracted many great students, such as Niels Bohr and Ernest Rutherford. About 10 years later, in 1890, he married Rose Elizabeth Paget, daughter of Sir George Edward Paget. They had one son who, like his father, was a physicist. In conclusion, J. Thomson's profound background served as a foundation for his future experiments. In 1894, J. Thomson and other investigators observed that when a current is passed through a cathode ray tube, the side directly opposite the cathode glowed at cause of a stream of particles, which they called a cathode ray, which is a glowing beam of particles that follows an electrical discharge in a high vacuum tube. In testing, Thomson found that cathode rays were deflected by a magnetic field, just like a wire carrying an electric current, which is known to have a negative charge. He noticed that the rays were deflected away from a negatively charged object. Here is a video showing the cathode ray as J. Thomson observed it.
This is a cathode ray tube. Inside, there's nothing inside. It's actually a vacuum tube, so there's nothing but a vacuum on the inside. And it's called the cathode ray tube because this is the anode and this is the cathode. When it's hooked up to an electric current, like I'm about to do here, you can see a beam moving across. You might think it's light, but when you say a magnet's a light, it doesn't do this. So you can see that it's bending or deflecting away from the magnet, so we know that it's not actually light. What J. Thomson summarized was that he was seeing a piece of an atom flying from one end of the cathode ray tube to the other, and that the piece of the atom that he was seeing was negative based on the end of the magnet that was causing a repulsion. So the negative end of the magnet was causing a repulsion, therefore the particles must be negative.
This investigation led to Thomson becoming the first to suggest that the fundamental units that comprise atoms were at least 1,000 times smaller than the actual atom. These fundamental units are now known as electrons. Through his experiments, Thomson acknowledged that the electron had a very large charge-to-mass ratio. In 1909, Robert A. Millikan measured the charge of the electron. With this information and the charge-to-mass ratio, Thomson observed that the mass of the electron is about 1/2000th the mass of the simplest type of hydrogen atom, the smallest known atom. After Thomson died, Cookson Rockwood of the scientific journal Rapid Communications in Mass Spectrometry suggested the use of the Thomson, which is a unit of measurement that describes the charge-to-mass ratio. He concluded that these particles, to which he gave the contemporary name of corpuscles, were negatively charged and virtually weightless. With all the knowledge of electrons, it was inferred that because atoms are neutral, there must be a positive force in the atom to supplement the negative charge of the electron, and that because electrons are so small, there must be other particles in the atom. These inferences disprove Dalton's fourth statement in the atomic theory that atoms cannot be subdivided. To summarize his findings, Thomson developed the plum pudding model. This name was derived from the English dessert. Thomson believed that the electrons were evenly distributed throughout the atom, as the plums were evenly distributed throughout the pudding. These subatomic particles can also be compared to watermelon. Although the seeds in watermelon are dispersed throughout the fruit, they do not significantly contribute to the overall mass of the melon. It was this discovery that introduced the concept of the electron to the current model of the atom. The document shown is an article written by Thomson in Harper's Magazine. In the article, he summarizes his experiment with the cathode ray and expresses his interpretation of the results. His conclusions were enhancements upon John Dalton's previous model of the indivisible atom, which stated that atoms could not be divided into different subparticles. Although the addition of the electron to the atom was an improvement on Dalton's earlier addition, J.J. Thomson neglected to properly place the proton in the atom, which was later added in Ernest Rutherford's nuclear model. After making many contributions to chemistry and physics, such as the mass spectrometer invention and helping to discover isotopes, J.J. Thomson died August 30th, 1940, and is buried in a fellow mathematician and physicist Isaac Newton and physicist Ernest Rutherford in Westminster Abbey. And that brings us to the end of the video. Thanks go to Mariam Muhammad for research and editing, Kirsten Taylor for research and time coordinating, and Toyini Dogan for research and design.